This presentation is a continuation of our discussion of floating point number representation. We want to consider adding floats. Let's consider it first in scientific notation. Let's add the number 3.456789 times 10 to the 3 and 1.212121 times 10 to the minus 2. Our first step towards adding these two numbers will be to re-express the smaller number in a form in which it will have the same exponent as the larger number. So the smaller magnitude number was 1.212 times 10 to the minus 2, and we want to get it to have a power of 10 to the minus 3. So we're going to make the power larger, so we must make the number out front smaller. And so we keep, as we raise the power of 10, we shift the number in front and make it smaller. So we must do that a total of 5 times. We want to go from minus 2 to 3, so 3 minus a minus 2 is 5, so we need to change this by 5 places. Once the two numbers have the same power of 10, then we are in a position to just add the numbers in front. So as we prepare the two scientific notation numbers to be added, we picked on the smaller number and we shifted it until we got two numbers with the same powers. But remember that in computer science, there is always a finite number of bits being represented at any one time. So when we take that smaller number and we are shifting it to make the exponents equal, we are losing information on the very low end of the low number. That's why we choose to pick on the low number, because that's the information we want to lose, the low end of the low number. If you're going to lose information, that's the information to lose. But you must realize that you are losing that information, and this is known as rounding. You should know from your high-level programming language is that you never should test on the equality of floats, and this is why the slightest operation, the simplest operation on a floating point number might cause there to be some rounding, and therefore what should be in actuality two equal floats could very easily, one could be rounded and they will no longer be equal. So it's never a good idea to test on equality of floats. So we remember that in floating point representation, there is in the mantissa a 1 that is implied that is not stored. So we would have, when adding two floating point numbers, we will have the same situation that we had in the scientific notation, except with the additional problem of the implied 1 that has to be brought in. But you will still have the shifting, and you will still have the loss of information, you will still have the rounding. One problem with having this implied 1 in the mantissa is that we lose the number 0. So if that first digit is always implied to be a 1 and then it's multiplied by some power of 2, some number that's 1 or larger than 1 times some power of 2, there's no way for that to get to be 0. But 0 is far too important for us to lose. So we must have a special series of bits that is going to correspond to 0. And so if the mantissa is all 0 and the exponent is all zeros, that is 0. So we need to have these special cases, and 0 is a very important special case. Remember that we biased by 127 because we were sort of stealing 1 from the positives and from the negatives so that we could have an exponents of all zeros be reserved for some special cases, and the same thing for all 1s. Two other special purpose floats are what we call not a number and infinity. So again, special representation, special binary strings in the floating point representation that have these unusual interpretations. But we're going to focus on sort of the regular old floating point numbers and not worry too much about the special cases. So let's consider an example. Negative 9087.8735. Let's try to represent this as a floating point number. Floating point numbers are going to use 23 bits for the mantissa, 8 for the exponent, and 1 for the sign. But remember that the float, there's an implied bit. So we're going to work with 24, get a representation with 24 bits, and then just sort of not store the first one. So we're going to start with the whole number, 9087, and we're going to represent that in binary. That's 10 00111, 0111, 1111. And we see that that takes 14 bits, and the mantissa with the 1 implied is 24 bits, and we've used up for the whole number part so far 14 of them, so we have 10 left. So we have 10 bits remaining for the fractional part, so we're going to take our fractional part, 0.8735, and multiply it by 2 raised to the 10. That's getting us 894.464. We're just going to take the integer part of that, the 894, and represent that in binary, which gave us the binary string. And then we see how many bits that took, and we see then it is taking 10. If it did not take up 10 bits, we would need some leading zeros. The leading zeros would be, the first leading zero would be the halves place. We don't have anything here, and that makes sense because our fraction, 0.8735, is larger than a half, and so we expect a 1 in the halves place, so we don't expect the need for any leading zeros in this case. So far, the whole number took up 14 places, and we're using 10 for the fractional part, but now we play our scientific notation-like game, and we want to move that dot up to the point, so it should start with a 1 and then the dot. That's our game. And then that makes it move 13 places. So we had, the whole number was 14, but we're moving the dot so that it's 1.000. And so we move the decimal place 13 times. To compensate, we multiply by a power of 2 to the 13. So we have now our mantissa, which is the first bit is implied, the first bit before the dot is implied, and all the 23 remaining bits are stored. We know that our power of 2 is 13, which we must bias with 127. So 13 plus 127 is 140. That's what we will store for the exponent. The overall number we were representing was negative, so our sign bit is a 1. And then when we put all the pieces together, we store the sign, then the exponent, then the mantissa. We're going to the website with the converter, and we're putting in our found float. So our sign bit was 1, our exponent was 1,000,1100, and then our stored mantissa started off 00011, etc. And we see that the decimal representation is minus 9087.873, close to our starting number. So let's, in our second example, consider a number that is less than 1, 0.00766534. There's no whole number part, so we're going to take all 24 bits and use them for the fractional part. So when we're dealing with the fractional part, we take our fraction, 0.00766534, and we multiply it by 2 to the number of bits for the representation of our fraction. So that was 128402, etc. And we take the whole number part, the 128402, and represent it in binary. And we see that it uses 17 places. So we expected to have a 24-bit fraction, and we got a 17 bits, and so that tells us that there are 7 zeros in the front. Now we have 0.70, and then we have our number starting 11111, etc., etc. Okay, and then we play our scientific notation game where we want it to start with the dot after the first 1. And so we see that we must move the dot, in this case, 8 times. We are making the number bigger because we move the dot to the right. So to compensate, we multiply by a negative power of 2, so times 2 to the minus 8. So now we know our exponent, our power of 2, to get us our exponent. And we have the beginning of our mantissa, but we don't have our full mantissa. We expect our mantissa to have 24 bits, one of which is implied. and so 23 bits. But of our 24 we are expecting, we only have 17, so we have to go get more digits for our Mantissa. So the way we'll do this is we'll basically start again. So we'll take our fraction 0.0076534, and now we're going to multiply it by 2 to the 31. 31 is the 24 plus the 7 we're missing. That gives us 164355551, etc. And when we express that whole number part as in binary, we get 24 bits. And we will see that the first 17 bits agree with what we had before. So now we are ready. So we have the Mantissa with the implied 1. We have our exponent, which was a minus, the power was minus 8, and we bias it with 127. So 127 minus 8 is 119. And the overall number, sign of the number, was positive, so the sign bit is 0. And here again, going to the website, we are showing our check. So we use the little check boxes to put in our floating point expression, and we see that the decimal representation that comes out of the converter is close to our original number that we were representing. So now let us consider the reverse process. So we're starting with a floating point representation, which is 32 bits shown at the top. We break it into the 3 components. The first is the sign, then the exponent, then the Mantissa. So that very first bit is the sign bit. The sign bit is a 1, so the number represented is going to be negative. The next 8 bits correspond to the exponent. It's shown in green. It's 00001111. That corresponds to 15. But to get to the exponent, we took the power of 2 and we biased it by adding 127. So now we must, to get to the power of 2 from the exponent, we must unbias. We must subtract 127. So we take the 15, we subtract 127 and get minus 112. The 23 remaining bits are the Mantissa, and remember that there's an implied 1, so I show in the Mantissa the implied 1 in black, and then the blue numbers are the numbers that were stored, the 23 numbers that were stored. Now we must find out what the Mantissa is and finish the job. Okay, so we have our 23-bit Mantissa plus our implied 1 that goes in the front, and remember what it looks like at this stage. We think of it as one dot and then all of the stored numbers. If I multiply by 2 to the 23 and divide by 2 to the 23, I'm doing nothing. Those two things cancel each other. But if I take the 1.01 etc., 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 and multiply it by 2 to the 23, I can think of that as moving the decimal place 23 times. So I will get now just a whole number, and then I divide it by 2 to the 23. So I'll take that number, the 24 bits, find out what it is in decimal, divide it by 2 to the 23 in my scientific mode, and get a number. That number should be between 1 and 2 if I do this right. Remember where we started, 1 point something. So the number's clearly bigger than 1, and it's also clearly smaller than 2. If it were 2, it'd be 10 something. So we need a number. This process, to be, if it's done correctly, will get us a number more than 1 and less than 2, and that works out. So let's put the pieces together. The overall number was negative, so that's the minus sign out front. The Mantissa gave us this 1.318, etc., etc. And then we multiply that by 2 raised to our power, our unbiased exponent, which was minus 112. And so here I'm using Google as a calculator. So I put those pieces together and put it into Google, and the calculator popped out a number in scientific notation. So E is the calculator's version of scientific notation, so that E minus 34 corresponds to times 10 to the minus 34. And so I've got my number now in scientific notation. It's a very small number. Should I panic? No, that's the whole point of floating point numbers, is that they are meant to express very large numbers and very small numbers. So I should not panic if I see something very big or very small when I am taking a float and sort of reversing the process. So here, again, at the website, the converter, we're putting in the original floating point number that we were given, the ones and zeros, and we see that its decimal representation corresponds to what we found. Now, we said not to panic if the number ended up to be very large or very small, because that's what floating point numbers were for. But to really make this idea more precise, we should know what the range of floating point numbers are. And so a big float corresponds to 2 times 2 to the 127, giving us 3.4 times 10 to the 38. And a small float roughly corresponds to 1 times 2 to the minus 126, which is 1.175 times 10 to the minus 38. So expecting numbers, reasonable numbers to get, are between 10 to the positive 38 and 10 to the negative 38, are very biggest numbers and very smallest numbers we should expect from this process. So if we got numbers outside of this range, then we should panic. And here we're just showing some of the references used to put this talk together.